Okay, hello. My name is Pius, and I will be presenting our work on tiering in contraction and edge hierarchies for stochastic route planning. So, the standard deterministic routing problem looks like this. We are given a graph with vertices and edges, and to each edge, we assign a static real numbered edge weight. Let's assume for now that edge weights here represent the travel time on a given edge. A problem with this model is that the travel times on each edge of the graph are assumed to be exact. In the stochastic settings, each edge of the graph is labeled with either probabilistic functions or discrete histograms. These functions or histograms can be derived from past travel times of vehicles that have traveled along those edges. Now, arguably, the stochastic approach is a much more accurate model of reality. Not all vehicles traveling along the same edge can be assumed to take exactly the same amount of time to traverse the edge. But stochastic routing turns to be a much more complex problem. While the deterministic routing has a straightforward objective, that is to find the shortest path in a graph, it is not immediately clear what the shortest path in a stochastic graph even means. Perhaps not surprisingly, there's a wide array of prior work on defining meaningful objectives for routing under stochastic settings. Here, we are interested in three definitions of the shortest path. One that minimizes the mean risk objective, finding the Pareto set of all the best routes between the source and the destination, and the probabilistic budget routes. I shall come back to the precise definitions of these three objectives in a little bit. Now, to understand what makes stochastic routing particularly difficult, let's say we have a graph with just three vertices. The edge weights of AB and BC are assumed to be 5 and 3 units respectively. Then the total edge weight from A to C is 5 plus 3 or 8 units. However, when the edge weights are labeled with histograms, the total distance between A and C can only be given by the convolution of the histograms on the two edges. The expensive convolution operation that needs to be applied between histograms is the biggest challenge in stochastic routing, and it is the one that prevents it from being deployed much more ubiquitously, in spite of being a much more accurate model of reality. Finally, there's a large number of speed-up techniques that have been developed for deterministic route planning, like contraction hierarchies, customizable route planning, hub labels, CCHs, and so on. Applying similar techniques to stochastic routing is relatively understudied. Before I get to the tiering idea of a paper, it is important to understand how contraction and edge hierarchies actually work. Broadly, it works like this. The contraction operation is defined as follows. If the shortest path from a vertex U to a vertex W goes through a vertex V, then we can add a shortcut edge that connects U directly to W. And we can remove the vertex V from the graph. Similarly, to construct an edge hierarchy, if the shortest path from U prime to V prime goes through an edge UV, we can add one of the three listed shortcuts without affecting the correctness of our algorithm. So we can add one of U prime U, V V prime, or U prime V prime. And we can remove the original edge, the UV, from the graph. This gives us an algorithm to construct a CH or EH on a given graph. First, we order the vertices or edges in their increasing order of rank. Then, we contract the vertices or the edges. And finally, we can add all the shortcuts derived from this procedure to the original input graph. Now let's go back to the stochastic routing settings. In the paper, we are concerned with the following three definitions of shortest stochastic shortest paths. First, the non-dominated routes, which is perhaps the most straightforward. We want to find routes between S and T such that they have edge weight distributions that are not completely dominated by other routes. We want to find probabilistic budget routes that maximize the probability of travel cost being within a budget B. And finally, the mean risk routes, where the user gives us a risk aversion coefficient C, and we want to find routes that minimize the mean travel time plus C times the standard deviation. Now, prior work has applied contraction hierarchies to speed up stochastic routing queries. The essential idea that our paper introduces is called tiering, by which the hierarchy being built is divided into tiers, and in each tier we use an appropriate edge weight representation that minimizes the cost of computing convolutions, number one, and number two, ensures that the representation is as compact and space efficient as possible. Using the tiering technique, we propose uncertain contraction hierarchies and uncertain edge hierarchies, both of which use two tiers. At the lower levels of the hierarchies, we use histograms because they are much more likely to represent the actual distribution more accurately, but they have a higher convolution cost. However, at higher levels, the shortcuts represent longer distances and thereby have edge weights that, because of the central limit theorem, more closely resemble the Gaussian distribution. Therefore, we can simply replace the edge weight histograms for shortcuts in the upper tier with Gaussian distributions without much loss in accuracy. A challenge here, though, is determining the appropriate boundary between the tiers of the hierarchy. So to determine the appropriate boundary, we use the following method. After every lambda contraction operations, we check if the edge weights of the shortcuts being added are sufficiently similar to a Gaussian distribution using a similarity measure. We can use a KL divergence or a Hellinger distance. We consider the KL divergence and the Hellinger distance measures in the paper. If the edge weight and a Gaussian distribution are found to be sufficiently similar, we make the vertex or the edge being currently contracted the boundary between the tiers. Using the two different similarity measures gives us two variants of uncertain contraction and edge hierarchies. We call them the KLD hierarchies and the HD hierarchies. We tested our method using real-world edge level traffic data extracted from Mapbox traffic dataset between July and November 2019. Our graph has approximately 250,000 vertices and approximately 500,000 edges. We found that applying tiering to contraction and edge hierarchies reduces the pre-processing times for both KL divergence and Hellinger distance variants of the CH and EH by as much as 37%. Further, we also observe that applying tiering improves the performance of finding non-dominated routes and probabilistic budget route queries by up to 3 times in certain cases. Lastly, these graphs show the improvement in performance for mean risk routes for different values of the risk aversion coefficient. A key finding of our experiments is that under stochastic settings, the edge hierarchies perform nearly at par with contraction hierarchies. This is in contrast with the previously known results where contraction hierarchies were known to be much better than EHs for all known cases. Our results can be attributed to the EH query algorithm being much more selective in relaxing edges than the CH query algorithm. Now there are several other details in the paper, including theoretical bounds on the rate at which the convolutions of histograms converge to Gaussians. And there's also a bound on the maximum approximation error that you can get on the three kinds of routing queries when using the Hellinger distance metric. I invite you to check out the paper for more details. Thank you so much.